Okay, good afternoon, everyone. Welcome to the third lecture of EfficientML.ai. Today, we are going to jump into a very important topic about model compression, which is pruning and sparsity. We will have two lectures that covers pruning and sparsity, since this is a pretty important technique, and this will be the first lecture. So today's AI is too big. We have seen this figure. A lot of compute to achieve high accuracy, and we want to bridge the gap between the supply and demand of efficient AI computing. So part one of this course will be about efficient inference, and we will have four major pillars. Okay, the first pillar is about pruning. We are going to spend 2 lectures about that. Lab 0 is already out, so Lab 1 will be about pruning. It will be out by next week. Okay, so keep an eye on the homework. And then we're going to have another 2 lectures about quantization. Okay, so this is next Tuesday. Lab will be out by Tuesday. And then the third part will be neural architecture search. Okay, neural architecture search followed by knowledge distillation. Okay, we will have lab 2, which is about quantization. Okay, on September 28th, followed by the third lab, which will be related to neural architecture search, which will be out at that time. And after the student break, we'll have MCUNet to talk about how to further squeeze the neural networks to microcontrollers. Tiny little microcontroller can buy at $5, together with the tiny engine, the tiny inference engine that can actually deploy the model on microcontrollers. So that will be the schedule for the first part of this course, to give you just an overview. So let's start with some motivation. Okay, so let's first introduce this MLPerf benchmark, which is the Olympic game for AI computing. So many companies participate in this competition every year. So the latest season of MLPerf just concluded last week. NVIDIA, Google, AMD, Intel, lots of the companies participates in this competition. Measures how fast your hardware, the algorithm can run a particular workload at a particular given accuracy. Okay, so there are 2 tracks, 2 divisions. One is the closed division, the other is the open division. So the closed division basically says you cannot change the neural network. You cannot change the precision. You cannot change the number of weights. You have to run it exactly as is. Just use hardware innovation. How many samples per second you can achieve. There's also the open division. As you can guess from the name, you can openly try different ideas, different innovations on changing the model. For example, you can prune the model, you can compress the model, you can reduce the precision, you can do all kinds of tricks. As long as the accuracy is well maintained, then it's considered a valid submission. So we can see in the closed division on the same hardware platform, we can achieve 1,029 samples per second. While in the open division, if we are given the freedom to further optimize the model, we can achieve more than 4,000 samples per second. That's 4.5x faster. Okay, so the same hardware, you immediately reduce the cost, immediately make it faster. So we are going to learn these techniques. Okay, so how did NVIDIA achieve that? Okay, there are 3 major pillars, which is quantization, aware training, pruning, and also distillation. Okay, if applying this quantization alone, maintaining 99% of accuracy, the model size is about 600 megabytes, and the speed up is 1. Combined with pruning, which we are going to learn in this lecture and also next Tuesday, it becomes 2.6 times faster. Okay, the model size is also reduced a lot. Finally, by distillation, we can use the distilled loss to recover the accuracy from pruning, combining pruning, distillation, and QAT. We can make it 4.5 times faster, okay, which is pretty impressive. So that motivates why we want to learn all about this, about pruning. So today, we're going to first introduce the concept of neural network pruning, what it is, and how much we can prune, almost 10 times smaller, make it faster, more efficient, followed by different steps of how do we do pruning. Okay, what are the granularities we do pruning? What is the criteria we can prune the neural networks? Okay. So some basic motivation is that the memory is expensive. We want to reduce the memory access as much as possible. So a 32-bit add in 45 nanometer takes about 0.1 picojoules, which is pretty cheap. Even the floating point add is 0.9. Accessing register file 1. Multiplication slightly more expensive. SRAM access, cache access slightly more expensive. But as soon as you go to the DRAM, okay, as you go to the DRAM, it becomes 2 orders of magnitude more energy consuming. Okay, so it is memory reference that is draining the battery of our phones. So therefore, we want to reduce those memories, including both the weight and also the activation. Okay, if you can reduce the amount of weight of a neural network, you can save the DRAM access and save the power. Therefore, the battery can probably last longer. Okay, so what is pruning? Pruning basically turns a dense neural network into a sparse neural network. You can remove those redundant synapses, and also you can remove those redundant neurons. Okay, it becomes less redundant. So this study shows the number of synapses in our human brain. Okay, so a newborn child has about 2,500 synapses per neuron. When he or she grows about 2 to 4 years old, this number quickly surges to 15,000 synapses per neuron. Interestingly, this number didn't keep increasing as the child grows to adolescence. Actually, adolescence is a period when we go to school and learn most of the knowledge in our life. But interestingly, the number of synapses actually begins to decrease during this period. Okay, so the pruning process happens. You first have a lot of synapses per neuron, and then have less until it stabilizes during for adults, stabilizes to about 7,000 synapses per neuron. Okay, so this pruning process naturally happens in the human brain. And similarly, we can do I carried out this experiment back in 2015 for modern neural network for AlexNet. So basically, we remove those small connections, very simple criteria. If it is small, then we remove it. Remove it means setting it to 0. Okay, since 0 multiplied by anything is still 0, we don't need to compute on it. We don't need to store it. Then it saves the memory and saves the computation. Any questions?
Just to say, going back to the biological example, it really only showed pruning of synapses, not removal of any neurons. So do you see in practice for the network that removing neurons is stronger or removing synapses is stronger?
Yeah, we'll cover both pruning the synapse, pruning the weights, and also pruning the activations. And also tell the relationship where if you prune a neuron, you basically prune away all the weights associated with that neuron, so they're not independent. Okay, so let me start with the experiment I did in 2015, starting with the AlexNet that has 60 million parameters. Okay, so here, this is the original weight distribution. We train the model, make it converge. And this is the original baseline accuracy. As we remove those small connections, those small weights, and we can see the accuracy begins to decrease. Okay, so especially if we observe the weight distribution, those small ones are removed. Okay, the more you remove, the less the accuracy. When you remove 80% of the parameters, how much accuracy you lose? 4.5% accuracy is lost. So people design AlexNet or different neural networks just to improve the accuracy by like 1 or 2%. Suddenly you lose 4%. That is not good. Right? Can we do better? So we can fine-tune the model. Okay, given this model, exactly the same sparsity ratio. These connections are dead. These are still alive. Okay, so we want to fine-tune the remaining weights to recover the accuracy. Actually, we can do a very good job until like 75%. Almost no degradation of accuracy. Sometimes even increase accuracy a little bit due to less overfitting. Okay, so what is the distribution like? In this moment, becomes flatter. Okay, since the weights they have the freedom, they have the degree of freedom, they can adjust. Those weights, some of them move to the left, some of them move to the right, so that the accuracy gets recovered. Compare with just do it once. Okay, train it, prune it, retrain it. We can do this process iteratively. Prune it a little bit and then retrain it. And then we can further push the frontier to the right-hand side, to the top right corner. Okay, about 90% of the weights are pruned, while the accuracy is very well maintained. This is pretty amazing, where almost with no loss of accuracy, you can make a model 10 times less number of parameters.
Is there a way to predict the structure of the group network at the beginning and start training the model on this group structure?
Actually, you have to train it in the beginning, at least for a while. There has been a study to see whether you can start pruning exactly at time 0. That's very challenging. You have to train it a couple of epochs.
Is this training accuracy or testing accuracy?
This is a test accuracy. Yeah.
If you tried adding just like an integer constraint saying like 90% of these need to be 0, and then you don't need to do an iterative one, because it could be the case that iterative approach gets like a local minimum, but if you do it one step, it'll say hey, with 90% prune, this is what we'll do.
Right. I tried directly give a very high pruning ratio, remove lots of connections, but the rest of the parameters is hard to recover the accuracy. Instead, if you go a little step, like from 50% to 40%, recover them 40 to 30, that works better than directly jumping from 50% to 30%.
I have a question. You say the time consuming is majority was in the reasons in the DRAM. So is that possible that we didn't print the nodes or the activation? We just combine the weights in the same DRAM. Like for a model, there will be say 100 nodes and so 100 weights, and we combine them 2 by 2 within 50 times or within of the DRAM. Is that possible?
Oh, it is possible. That is weight sharing. Right? 2 weights they share the same value. We'll talk about in the next Thursday's lecture.
And not necessarily to share the weight, but combine the weight in the same storage place.
How do you combine 2 weights in the same storage place?
We don't need all the 30 attributes.
Well, we can definitely use quantization. That's what we're talking next Thursday. Like use only 8 bits. So 32 bit, you can hold 4 weights rather than only 1 weight.
The coefficient of that weight would probably take up less based on the weight itself.
But we can have the weight consecutive.
Yeah.
So you don't have to explicit. But this one definitely, we'll talk about how to represent them later. So you need to represent the location of those weights.
So with the iterative pruning, is there like some place where like doesn't matter like how many iterations you're doing, you're just gonna converge to like a peak like pruning ratio to accuracy loss kind of thing, or is it just like we can iterate as much as we want and like it'll just be getting better?
Right. We find there's a very steep peak as soon as you pass the threshold, it's very hard, even you do a couple of more iterations, very hard to further prune it.
Just want to clarify that in this approach, when you are thresholding the weight and we're doing it layer by layer, so like sparsity ratio for each layer is the same, or like we're doing it globally, so that.
Oh, we'll talk about that in the later part of how to select the sparsity ratio in each layer, actually in the next lecture.
Is the pruning criteria the same for every iteration, or do you kind of change it, modify it?
We use the same L2 norm criteria.
Is your criterion for eliminating small weights, is that absolute in nature, or is it the magnitude of the weight relative to other weights in the same layer?
We sort them. You can either do it within the layer or across the whole neural network. In this experiment, I did it within that layer. Yeah, everyone prefetched a lot of questions. I'm going to cover in later part of the next lecture. That's good. You're thinking ahead of the lecture. That's good. Okay, and see, this is not like that, but there are also newer neural networks like VGG, GoogleNet, ResNet 50, and also SqueezeNet. This is when I collaborated with the UC Berkeley folks back in 2016. You can tell from the name, it's pretty small, like only 1 megabyte. So even for this small model that is very small to begin with, we can still compress it, right? But you can see the larger the model to begin with, like VGG 16, the larger the reduction ratio, you can have more room of compressing that. Or AlexNet, which is actually very redundant, you can compress it by almost 9 times, like ResNet 50. Or SqueezeNet, there's less redundancy. The model is more efficiently designed, but still there's room of about 3x room to further reduce it. So let's see, not only image, but also image and language. We can prune this image caption model. Okay, given this image, the original baseline says a basketball player in a white uniform is playing with a ball. And if we prune 90% of this model, it's going to say a basketball player in a white uniform is playing with a basketball. It's pretty much the same. Or this one, a man is riding a surfboard and a wave versus prune 90%. A man in a sweatsuit is riding a wave on the beach. Or if we prune too aggressively, like this one, the baseline says a soccer player in red is running in the field. But this got pruned by 95%. That's super aggressive pruning ratio. It says a man in a red shirt and black and white back shirt is running through a field. It's no longer correct. Almost getting drunk. So there is a right threshold we have to figure out. So those experiments after we did in 2015, 2016 becomes super popular in recent years. Lots of companies, both industry, academia, are using this technique to accelerate neural networks. Even recently on large language model, people are using sparsity to accelerate large language model. This line of research really started back in 1980s, where there's a paper called optimal brain damage that started this area. But the beauty of deep learning is that with more compute, with more data, with modern different scale, even the same principle, the same math that existed for decades can get reborn in the context of modern deep learning computing. So here's some adoption in industry. For example, this is my paper back in 2016, where we can try to design a hardware accelerator for sparse and pruned neural network without having to decompress it. So this efficient inference engine can take advantage of the sparsity, the weight, to skip those zeros, since 0 multiplied by anything is 0. So we can save the compute for both the sparse weight and also the sparse activation. This is a PGA prototype for ENE, and also this is a general purpose sparse matrix multiplication unit designed at MIT. So NVIDIA adopted this sparsity, this weight sparsity, since the A100 GPU. which delivers 2x peak performance and 1.5 measure the bird speed up. We are going to dive deeper in today's lecture. And also Xilinx is now part of AMD, adopted sparsity and pruning in their Vidas AI tool, which is basically coming from after acquiring my startup called DeFi Tech, which is now their Vidas AI platform, which can use pruning to reduce the number of parameters, reduce it by 5 to 50x with minimal accuracy impact. Okay, so given those big overview, let's dive a little one more layer deeper into what is pruning and how do we formulate that. Okay, so we have a loss function, the input and the weight. Okay, previously the weight is denoted as W, but after pruning we denoted as WP, P for pruned. We want to make sure the number of non-zeros is smaller than a target pruning ratio, a target number of non-zeros. Okay, so for example, you have 60 median parameters, your target 10% pruning ratio is n equal to 6 median parameters. Okay. So we use that to represent the pruned model, okay, using the same inputs, but the weight, loss of them becomes 0. Okay, so that's what becomes weight WP. And also the number of non-zeros should be smaller than a threshold. And then let's talk about how do we determine the pruning granularity. What is the granularity? We can, given this 4x4 weight matrix, we can either prune those individual elements, or we can prune a group of them, right? Like 2x2 or 2x1, at a coarse granularity. Okay, we're going to dive deeper than that. Just give you first to give you an overview, and what is pruning criteria? Which synapses, which neurons do we prune, and also the pruning ratio. How much do we prune? And finally, how do we recover the accuracy after pruning? So let's start with the pruning granularity, which basically says we can prune at different granularities from those structured to unstructured. You can imagine the structured pruning may have better hardware efficiency, but you can prune less, right? So we are going to learn those trade-offs. Given this example, we have an 8x8 2D weight matrix. Okay, so we can either do this fine-grained unstructured pruning where the non-zero location is completely random. Okay, those non-zeros can appear at either rows or either columns. It's you can have the most flexibility to prune your model, but it's hard to accelerate because it's irregular, and hardware parallel computing doesn't like irregularity. There are other approaches, right? Out of these 8 rows, okay, we can force the entire row to be a 0, to prune away the entire row. So out of these 8 rows, I prune away 3 of them. Okay, so we have only 5 rows left. What is good about this approach is that after pruning, the weight matrix is still dense, still a dense matrix. You can still utilize the dense matrix multiplication libraries provided by the vendor. So it's still a dense matrix multiplication, but it's definitely less flexible to prune. Okay? This way you want to prune it. Some of this neighbor you also have to prune it. Okay? So you have less flexibility than this approach, but this one is more regular. Therefore, it's easier to accelerate, just as given it a smaller matrix. Okay, so let's take a deeper look at the convolutional layer. Okay, in the last lecture, we talked about a convolution kernel. The weight of a convolution has 4 dimensions, right? So we have the input channel dimension, which is C in. We have the output channel dimension, which is C out. We have the size, the height and width of this kernel. Okay, so these 4 dimensions give us more choices compared with previously the fully connected layer, right? You just have C in and also the C out. now you have more dimensions. So let's see what are the pruning granularities choices. So remember, we have 4 dimensions, right? So this is this kernel size, 3 by 3 kernel. That's the first 2 dimension. We have the input channel. In this case, we have 2 input channels. We also have the output channel. Okay, in this case, we have 3 output channels. The fine-grained pruning is basically you can pick any of these from any of these dimensions. Any element could be 0. Okay. We can make it a little have a little more a better regularity to enforce some structures or some patterns. It's like a Tetris. Okay, you can enforce some patterns rather than this completely random pattern. Or you can perform this vector level pruning. If you prune, this entire row needs to be 0 or non-zero. Or you can do this kernel level pruning. This entire 3 by 3 kernel is either all 0 or all non-zero. Okay, we can go even more regular. The entire channel is either remain or prune. So we have this broad, very broad spectrum of pruning regularity for convolution operations.
Wait, what's the advantage of pattern-based? Like, what's the point of making?
Very good point. So NVIDIA is basically using this kind of pattern-based pruning. For you here, since you as a head, when we give it some pattern, it's no longer completely irregular. So look at this matrix. Do you see some pattern?
It's all 4, but we use it on controls.
Look deeper. Look deeper. What is some pattern here? Or some regularity here?
Corners.
Corners. Like 3.
Like that and then that. Like corners that look like this kind of.
That's probably overfeed. Yeah. You have a.
I can't.
Let's see.
There's like 4 greens in the row, right? So there's like 4 by 4.
So if you look at this 1 by 4, this 1 by 4, what's common? 2 of them. Only 2 of them are 0 or non-zero. So exactly for every 4 elements, 4 elements, only 2 of them are non-zero, and you have exactly 2 of them to be 0, right? So what's the sparsity ratio? It's 50%, right? So what is good about this? You can actually condense it in a way that each row, rather than 8 elements, now you have exactly 4 elements. It's still dense, but you have to pay some overhead to store the index. Okay? So among these 4 elements, 1, 2, 3, 4, we have 4 elements. Each element we have to specify which position am I sitting, right? How many choices? 1, 2, 3, 4. Each non-zero element can sit in either one of 4 choices. So how many bits do we need to represent it? 2 bits, right? 2 bits, right? So we need 2 bits to index to specify which is the location in the non-zero. For example, here, this one is 0, right? What is this? It's 3, right? What about this? It's 1, and this is 2. And so therefore, we need to store this indices as some actual overhead, but it's relatively small. Right? So this is what is utilized in NVIDIA's Ampere GPU architecture, which give you a 2x peak performance. Okay, hope that answered your previous question. And let's continue the discussion. We were here before. Okay? We were here before. This is the whole spectrum. And previously, we dived deeper into the pattern-based. And what are the pros and cons among different choices? So fine-grained pruning, the case we showed before, we can make it very flexible to prune. And we can usually have larger comparison ratio since we can have the flexibility to find individual redundant weights, okay? And sometimes you can get really high reduction about the number of weights. However, like we introduced in last lecture, the reduction in the number of parameters does not directly translate to speed up, right? So speed up also refers to whether it is easy to be parallelized and accelerated in hardware, right? So that's why we also have other pattern-based pruning. For example, when you have a certain pattern like this, we can use GPUs to maintain this regularity after you condense it, followed by the matrix. Okay. So this is available in the Ampere architecture, and we can observe for different benchmarks here, like Resin 50, the previously dense accuracy 76.1, sparse accuracy 76.2, very well maintained. Resin X 79, exception model, SSD for detection, mask, RCN, fair sick, transformer and BERT large across vision, and also these language models, these accuracy are pretty well maintained. And let's go to the other extreme, okay, the channel pruning. So for channel pruning is probably the most regular one, right? You remove the entire channel. So after that, you get a very dense matrix. For convolution, you just have one less number in the one of the dimensions, right? So this is easiest to accelerate, and for example, on your phone without any accelerator, or even on a Raspberry Pi, you do that kind of pruning, you can immediately get a reduction for the memory and also the compute. But the bad part of this is you can prune less, sometimes 30%. Okay, so that's the trade-off. This one like 9%, that's one like that's 9 times versus like 30%. Okay, so let's look into some cases about channel pruning, which is the last case. Although you prune, you can prune less, but this is very widely adopted in the industry. If you go to like a mobile AI company, this is probably the technique that is widely used, since it's just so easy to accelerate. So this is original different layers. You have 5 layers. Each layer has a certain amount of channels. You can just prune different channels to make it more have less number of channels. Given the same pruning ratio, the ultimate pruning ratio, the same ultimate pruning ratio, we can either uniformly reduce, shrink different layers, or we can wisely choose the sparsity ratio of different layers. We'll discuss in the next lecture how do we find the sparsity ratio for each layer. And just for the conclusion here in this lecture, this is the latency versus the accuracy trade-off. So which point will be ideal? Latency, accuracy, we want a low latency rather than high accuracy. So ideally at this point would be the best. So this kind of wisely choosing the pruning ratio for different layer is better than uniformly sample the different layer. Okay, so we'll introduce this technique actually done by our TAG. How to select, automatically select the pruning ratio. Okay, so now we want to talk about what is the pruning criteria. Okay, there are so many synapses and there are so many neurons that can be candidate of pruning. Then how do we select them? Okay, so we'll take a break, and then after that we'll jump into the section 3 to talk about the pruning criteria. Take a 5-minute break, returning at 4. All right, welcome back. So let's continue to talk about the section 3, which is the pruning criteria. So what synapses and which neurons should we prune? Okay. So let's see this example. Okay, so we have a simple multi-layer perception. that has 3 weights, W0, W1, W2. We combine 3 inputs together and pass it through an activation function. Okay, so imagine the 3 weights, we have 10 minus 8, 0.1. So this simple one layer perception is basically 10x0 plus minus 8x1 plus 0.1 x2. So by intuition, if only 1 weight will be removed, which one are you going to remove? Intuitively, the smallest one. Right? So actually, that's exactly the starting point about selecting which synapses to prune, basically based on the magnitude. And also that's exactly what I did in 2015. So we try to find a very simple way of pruning those connections. Like you have 4 weights, then you just calculate the magnitude. Okay, so we just find the magnitude, and these 2 are pretty large, 3 and 5, 1 and 2 are pretty small. So we keep those larger ones. So this seems super simple, but interestingly, that's the method that is adopted by industry for the past 5 years. Right? So a lot of fancy techniques, we always want to find a trade-off between the effectiveness versus how easy it is to integrate into a product. Right? So doing some research versus something that is really be able to land into product, they have a very subtle relationship. Right? So I usually tell the people that how to define the effectiveness. That's basically the accuracy or the performance divided by the complexity. Okay? If the code is super complex, you need some predictor, you need all kinds of complicated stuff. That's very difficult to make it into products. There are other methods, right? For example, we talk about different pruning granularity. Okay, so this example we prune at the fine-grained pruning, right? So here we have the flexibility to prune individual weights, but now we want to prune a whole row of weight. So for magnitude-based pruning, how do we generalize that to coarse-grained pruning? Very simple heuristic here, we can just sum up the absolute value across different rows, right? So 3 parts, 2 is 5. And here we have 6, just summing them up. And we've pruned away the smaller magnitude. Okay. There's another criteria when we are doing coarse-grained pruning that involves multiple elements here. So here we have 3 and 2. Now we can calculate the L2 norm rather than the L1 norm. Okay, so previous example, we are calculating the L1 norm. So this is the L1 norm. Just summing up the absolute value, we can also perform the L2 norm magnitude-based pruning. So we can calculate the L2 norm of 3 and 2, very simple math, and we can prune away the smaller one. And turn out L2 norm and L1 norm, they give the same result. Okay? Both of them are pruning the first row. So in general, there is the LP norm. Okay, so Wi to the power of P, sum them up together, and then to the power of 1 over P. Okay, so that is a more general heuristic. Are there more better approach for convolutional neural networks? So in convolutional neural networks, we have many filters. Okay, question here.
The singular value threshold help in this kind of thing?
Which value?
Singular value threshold.
What do you mean?
So take the weight matrix and find a low representation of it to make the weight 0.
Oh, so that is basically low rank approximation. So low rank approximation is orthogonal to pruning. So you can definitely remove those, just keep a few rank, like recently in LoRa, in large language model fine tuning, that is a very widely used approach. You can also actually think about it as a special case of pruning, but not necessarily the same, because if a weight matrix is low rank, you multiply them together, the dimension is still the same. So usually people talk about like pruning, quantization of low rank and distillation as 4 different techniques.
That is right. Following up on what you said, if it's low rank, and you force fitting certain elements to it.
That's why I say that those are orthogonal techniques. You can prune on top of a low rank matrix, and also you can quantize on top of a pruned matrix. And you can use distillation to supervise pruning, quantization, different losses. All right, so actually we can learn a scaling factor if we are doing channel pruning. Okay, so we multiply the result of this whole channel. Okay, maybe like 256 by 256. We can multiply it by a scaling factor. Okay, so when we are doing the learning, we want to encourage this scaling factor to be as close to 0 as possible, using either L2 regularization or L1 regularization. Okay, and then when we are doing pruning, we see the absolute value of the scaling factor. If the scaling factor is pretty small, then we prune those channels. So here is an example. This is before pruning. We have 1, 2, 3, 4, 5 channels, and these 2 are pruned. So we are only left over with those big scaling factors. And luckily, this scaling factor is already there in the batch normalization layer, which if you remember, we covered batch normalization in the previous lecture. Okay, so we can just reuse the scaling factor in the batch normalization layer to determine which channel to prune. There's also the second order based pruning method. So if we dive deeper into the math, the change about the loss function would be, this is the original loss function given the input, given the original weight. And now we are given the same input, but the pruned weight equal to the original weight tensor subtracted with a delta. Okay, delta means you are changing from your original weight to 0. Okay? So according to the Taylor expansion, this is the first order term, this is the second order term, this is the third order term. Okay, so we neglect the last term. Okay, so the last term is removed, assuming it's pretty small, and then assume the natural causal has converged. So the gradient, the first order, is also removed. So we are only left over with the second order. And assume each parameter is independent, we can also remove the cross term. So we are only left over with this second order term. Okay. So remember this matrix and this annotation, which we're going to put it again here, right? So we just need to calculate the Hatching matrix. Okay, but Hatching matrix is difficult to compute. So finding the full solution, the exact mathematical exact solution is quite computationally heavy, since you want to do the second order derivative. So as alternative, people have derived the various approximations rather than computing the Hatching matrix. So I leave that to future reading. Okay, so previously we talked about weight pruning, and as the question in the beginning of this lecture, we also have the opportunity to prune those neurons, okay, both for a linear layer and also for a convolution layer. Okay, if we can find the neurons that is not important, the more accurate we can find them, the more accurate we can, the better performance we can get. So in this example, this second neuron is pruned. Okay, and I mentioned this highly correlated with weight pruning, because as soon as this neuron is pruned, all the weights associated with this neuron are all pruned, right? So this neuron pruning is basically a coarse grained weight pruning. The neuron pruning is basically a coarse grained weight pruning. Let's see, right hand side. Previously we have 5 input nodes neurons and 4 output neurons. So what is the dimension of the weight? 5 by 4, right? So 5 and 4. So we removed one of the output neurons, which corresponds to all the weights associated with that neuron is removed. So that is exactly the coarse grained weight pruning. Similarly, for convolutional neural network, rather than 2 dimensions, now we have 4 dimensions, right? Kernel height, kernel width, channel input channel, output channel. So we are doing channel pruning in the convolution layer. For example, 1, 2, the third channel gets pruned. That's the activation, right? Pruning the neurons. And also the 6th channel is also pruned, right? Corresponding to these two filters. And as a result, the third and also the 6th channel, they are pruned away. Okay, so that's also a coarse grained weight pruning. Therefore, neuron pruning is highly correlated with the weight pruning. So let's see an example of a convolutional neural network. How do we determine which activation to prune, which neuron or which activation to prune? So usually we have this redo function. What does redo do? If it's smaller than 0, the activation will be 0, right? So like in this feature map, it is 4 by 4. The resolution is 4 by 4. And here we have batch of 2. Imagine we have 2 images, right? So that's the batch dimension. And also we have the channel dimension. We have 3 channels. You can imagine like RGB, we have 3 channels. Okay, and imagine we have image 1 and this image 2 images. And now our task is to determine among these RGB, these 3 channels, which channel or which channel should we prune away, right? So one simple heuristic is to examine the number of zeros in the channel. Okay, but you have different batches, so we want to look at that holistically across different batch. Okay? So we want to first define what is average percentage of 0 activation, APOZ. Okay, so rather than giving a very complicated math description, I always would like to introduce by a simple example. Okay? So here, how many, what is the average percentage of zeros? How many zeros are there? We have 1, 2, 3, 4, 5. Okay, we have 5. This is channel 0. Okay, and also we have a second image, which is here. Right? So we look at also channel 1 to see for the second image how many zeros are there in channel 1. 1, 2, 3, 4, 5, 6. We have 6 zeros in channel 1. Okay, so we have 5 plus 6. Altogether, we have 11 zeros for channel 1 across 2 images. And in order to calculate the ratio, we need to divide it by the total number of elements. So here we have 4 by 4, we have 16. There's another 4 by 4. So altogether, we have 2 times 4 by 4. That's 32 elements. Okay, so that's the ratio for the average percentage of zeros in the first channel. Okay? And similarly, we can do the same calculation for the second channel and also for the third channel. Okay, for the second channel, 1, 2, 3, 4, 5. Okay, 5 zeros, 5 zeros. And here we have 1, 2, 3, 4, 5, 6, 7. We have 7 zeros in the second image. Okay, so we can calculate the average percentage of zeros on the second channel, which is 12 over 32. And similarly, we can calculate that for the third channel here and here, okay, which is 14 divided by 32. So given these 3 numbers of percentage of 0, which channel should we prune?
zero.
Channel 0,
Down two, and so those numbers.
channel 2. Right, channel 2, since channel 2 has a lot of zeros, so if you zero them out, you will have minimum change. Right, so we want to prune away the number of the channels which has mostly 0, right? And there's the largest ratio of 0, meaning that if you set all of them to 0, it will have minimum impact for the final result. So this is how do we do activation pruning. Okay. So by this time, we covered both the weight pruning and also the activation pruning. There's another way called regression-based pruning, okay, which try to minimize the reconstruction error of the corresponding layers output. So previously, we were talking about the loss, which is feed the input, you get the output, passes through the entire neural network, you get a final loss. So here, we are trying to examine the individual, one individual layer. Okay, you have the input, you have the weight, you have the output. And this is super helpful, actually, with the recent wave of large language model. You know what? You know why? Because they are so computationally expensive. Like 1.5 billion parameters. It's super hard to fine tune, to run through the whole network to reconstruct the weights by back propagating into each layer. So people designed a smarter way that can do it locally. You just look at one layer. Just look at one layer. You try to minimize the change before and after. Okay. So before you have a 2x4 input, large size of 2, and input channel, you have 4 input channels. And now you have a weight matrix that project 4 input channels into 8 output channels. And as a result, you have 2x8 output tensor. So whenever you learn a new neural network architecture, is super good to understand the channel, to figure out the channel dimension. So that's why rather than using math, I want to put it in visualization to give you an idea. So now we want to prune one channel. Okay? So rather than 4 channels, we want to reduce 1 channel. Why not prune this way? Because this is the batch dimension. First input, second input. In later part of this lecture, we can also talk about token pruning. Like in natural language, word is roughly, you can think about it as a token, right? So not all the words are equal. Some of them you can neglect it, but you can still understand the meaning of the sentence. So there's also opportunity to prune in this dimension, which we'll cover in a later part of this lecture. So first, let's now just assume we are pruning in the channel dimension. Okay? So pruning the second channel in the input means for the weight, the second channel also becomes useless. Okay? Since this dimension corresponds to this dimension in matrix multiplication. And how do we determine which channel to prune? So we formulate that as outer product. Okay, so outer product means we do this vector times this vector for this output dimension. 2x1, 1x2, 1x2x1, and 1x8. You get 2x8. So that expands to an intermediate output, which is of dimension 2x8. Similarly, the second channel also can multiply with the second channel of the weight and get a 2x8 intermediate output. Okay, and how many do we have to do altogether? We have to do 4 times first one, second one, and the fourth one. Okay, so that's why we are summing up different intermediate activations together. Okay, from C to 0 to Ci minus y. Okay. And we get different partial matrices. So the trick we do here is we want to, for each partial matrix, partial outer product multiplication, we want to have a coefficient that is learnable called the beta. Okay? Beta, if it is 0, it means we get rid of this channel multiplied by this channel, right? So we want to make sure the number of non-zero channels is smaller than a given threshold. Okay. So what we do here is that we can iteratively first fix the W and then learn the beta. Okay, and then we'll fix the beta to learn the W. Learn the W means we can adjust the weight to make it fit after the pruning. And so by doing this process iteratively, we can figure out which way to prune. So last year, when I talked about this, large language model was not that popular, but given the context of large language model, this kind of technique would be quite interesting since you don't have to back propagate all the way to the end, which require like a super big GPU. But here we can just solve, reconstruct the weight, you know, for individual layers. But you can imagine this has drawback, right? You may not have a full holistic picture about the entire neural network. You're just reconstructing one individual layer. So always there's no free lunch. That's the beauty of efficient deep learning computing.
Sure. So isn't that really similar to the PCA because we want to minimize the reconstruction area, like what you mentioned, really similar to the ultimate encoder.
The reconstruction, we mean really fine tuning the weight. So it's not exactly the PCA stuff.
I mean,
So
because PCA is also minimize the error between the original dimension. And
oh, right. Using this iterative approach, right?
yes,
Right. Right. They are both done iteratively. So before concluding the lecture, I want to actually show a pruning demo, which I believe will be a lot more fun to see in practice. How do we prune a neural network? So let me move the screen to the left. All right. So let me reconnect. So here we prepared a MNIST data set. Okay, so for us to play with pruning and prune the net. So let's first visualize the demo images. So basically we are doing digit classification, like 0. This is the classification result. Like 3, this is the classification result. And now in this example, we are just visualizing the data set. It's just handwritten digits. And now we pre-train a neural network on MNIST. Number of data is not defined. Maybe I have to set up, run it from scratch. By the way, this is the Google Colab where the GPU is just in the cloud. Everyone can access. We are going to use Google Colab to do the homework. So if you haven't used it before, highly recommend you can try Google Colab. For example, try Lab 0 to make sure you're familiar with that. And also Google Colab has 2 versions. One is the free version, one is the paid version. I think the free version is enough for us to complete all the way from Lab 1 to Lab 3. Visualize the image. Now I train the model using the free version of the Google Colab. I think you get a relatively lower end of the GPU, but I think still the speed is still reasonable. If you pay $10 a month to purchase the Google Colab Pro, you can get a faster GPU. I think that's necessary when we are doing Lab 4, since we are playing with large language model, and I think it's worth to use a higher GPU. So it's doing the work. It's training for 1 epoch, and I think we're going to train like 4 to 5 epochs. Then it is going to converge. the accuracy is already pretty good. After one epoch is 98.05. After 3 epochs, 98.9. After 4 epochs, it's already 98.95, almost 99%. I think it's pretty much converged. Just give it one more epoch to make sure it converged. Right, it's pretty much converged. So now we can evaluate the accuracy of the original model before pruning. So we get 98.97. We can assume it's 99% accuracy. Given the digit, this is the prediction. They are all correct. So let's try to prune the model. So I give it a sparsity ratio of 70%, and let's see how that works. So using the pruning criteria, I remove a lot of parameters. We remove actually 70% of the parameters and only keep 30% of the parameter. And as we can see, the accuracy slightly dropped, right? Slightly dropped to 96.22. How about we increase the pruning ratio to 80%? Meaning that we are removing 80% of the parameters with only 20% of them non-zero. And you can see the accuracy immediately dropped to only 76%. And for example, here, given this image, it should be 8, right? But the pruned model says is 5. So let's see the power of fine-tuning. So I removed 80% of the parameters, and then I can do some fine-tuning for 2 epochs, hopefully to recover the accuracy. So the fine-tuning has started. This is the first epoch. Question?
Is the fine-tuning process just like more training or is there anything?
Right. The only thing we did is you mask away those parameters that's thrown away and fine-tune those remaining parameters. Other aspects are exactly the same.
So which pruning algorithm are you using? Is it just
Magnitude based.
that is not any of the channel based?
No, individual pruning way, individual weights, simple method. Okay, so sparse accuracy is already 99.89%. So let's evaluate the accuracy again on the test set. It's 98.89, right? Pretty much recovered the accuracy. And here, the digit 8 is now correctly classified as 8. Okay, so showing that although we are removing 80% of the parameters, it's still powerful enough where the remaining 20% is can fully recover the accuracy.
Oh, just curious, since the Google Colab doesn't have like the NP or whatever GPU architecture, like you would expect more speed up if you actually switch like a more modern GPU from this one.
Right, this one you have to pay it to use Ampere GPU, but in order to do that, you have to have the use their tool to make it a 2-to-4 sparsity.
Oh, I see.
This is the regular, irregular random sparsity. Yeah. So in order to achieve actual measured speed up, we need to, our next lecture, we'll talk about those techniques that can accelerate directly on sparse neural network. We can go more aggressive. We want to break it. So let's give it a higher threshold. Maybe 90%, only keep 10% of the weights.
Well, in the real life, we use the drop off instead of using the ensemble way to prune. Like in the architecture way, you use the drop off, you drop some node, you drop some.
Dropout and pruning are has different motivation. So dropout is designed to prevent overfitting for training, and pruning is designed for reducing the computation for inference.
But we can use ensemble pruning to replace dropout.
What do you mean by that?
Like we pruning in different ways, like a vector way and a channel way, and then combine the result as and example the result.
But you're adding two sparse matrix, you get a denser matrix. Adding two sparse matrix, you get a denser matrix. That's different.
Just off of that question, thinking about how I think when you're pruning, you're effectively exploring all available parameters and then selecting what are most efficient terms of final result, as opposed to dropout. Yeah.
Yes, dropout during different iteration, you drop out different weights. So in the end, you still get a dense weight.
Right, but just noting in the performance of the final model, if you're using dropout instead of pruning, you are not exploring the full set of available weights to get a fully optimal model. Is that the correct way to understand that? Like,
Also, different iteration, you are dropping out different stuff. So I rely on the fully dense model in the end to do the prediction.
Right.
So dropout is for training, but pruning is for inference. So let's see, after we remove 90%, the accuracy is only 20%. And let's try to fine tune it for two epochs and see how much it can recover. And by the way, this will be the starting code you can reference using when you are doing the homework one, which is basically going to implement this pruning process, this fine tuning process, which will be pretty fun.
So if we use size, shouldn't the epochs be faster as well?
Actually, this thing we didn't get we're still just masking away those weights. So you are doing all the computing. We talk about how to get measured speed up. We have to write special kernels. Okay, so after two epochs of fine tuning, let's now test the accuracy. Evaluate on test set is 98.5%, which is actually pretty good. So we can do it more aggressively until we make it. Let's make it 95%, maybe 99%. I'm sure it will break. Okay. This is wrong. This is wrong. That's as expected. Yeah, it's predicting everything at school. I think it's actually better than random because at least everything two, you get a 10% accuracy. And accuracy should be very close to 10%. Right, the accuracy is like 10 points, like 32. Exactly as expected. So let's test the accuracy after fine tuning. Oh, it's only 25% increased, but cannot fully recover. We broke it, right? So probably that's the limit. Okay. So hopefully you can use this code base to help you to finish homework one. And also you can use the code base for final project. For example, you want to explore other aspects of pruning, right? How does the pruned model generalize? Is the pruned model easier or harder to get adversarial attack? For example, those are the other aspects you can play with by doing surgery on the neural networks. Okay. All right, with that, I think that's all for today's lecture. Thank you. See you next time.